continue with NMR spectroscopy. In this we have done basic details. Now this we can explain with this figure. In this figure, this is a nuclei which acts like a bar magnet. Now when it is placed in a strong magnetic field like this, then this nuclei with a magnetic moment spins. That is, it has a spin magnetic moment, and when it is present in the magnetic field, it has two energy states. This is a low energy state and this is a high energy state. And now, and here it spins like in lower side it spins like this, and the upper side it spins like this. Now, and it rotates, and its rotation is preferable in the lower energy state. That is, north will remain towards south most of the time, and it will have lower energy state. And in the high energy state, the south will remain towards the north, and it will spin in this direction less preferably. Means it will rotate by 180 degree also, but most of the time the north will be towards the south, and this is a lower energy state. And so the average rotation of the magnetic moment will precess around the field, and this external magnetic field can be supplied by a large magnet or also by other nuclei in the unit. And this will also show the working, how it is spinning actually in later on spectroscopy. When we observe the spectrum, NMR spectrum of a molecule, in this the instrumentation is the main components of the instrument by which we record the NMR spectrum is. It consists of 9 major parts. First is sample holder, which is a glass tube which is 8.5 cm long and 0.3 cm in diameter. Then the magnetic coils, which generates magnetic field, and then permanent magnet, which provides homogeneous magnetic field at 60 to 100 megahertz. Then sweep generator, which modifies the strength of the magnetic field which is already applied. And then radio frequency transmitter, it produces a powerful but short pulse of radio waves. Then radio frequency, which helps in detecting receiver radio frequencies. Then RF detector, then recorder, which records the NMR signals which are received by a RF detector, and then a computer that records the data, that is, which gives out the spectrum. So this can be shown in a figure, that is this. In this, this is a sample tube in which the compound or molecules is placed in a suitable solvent, and then this is a source of radio frequency which is generally 60 megahertz, and then is a strong magnetic field which has 1.41 Tesla, and then this radiations when falls on this through a coil, and then this sample of which it absorbs the radiations from this are detected by RF detector, and then they are recorded. So this is a simplified way in which we can show how the instrumentation is done for a molecule to obtain NMR spectra, by which we can actually determine the structure of a molecule. So for any nuclei, what is the magnetic field required and radio frequency required to absorb hydrogen nuclei such fields? We have a general calculations by a Lamar equation, that is omega naught is equal to gamma p naught, or we can say nu is equal to gamma h naught over 2 pi. In a field B naught, that is 1.41 Tesla, the resonance frequency of hydrogen would be, that we have already done in instrumentation, that is 60 megahertz we provide radio frequency. So if this is the magnetic field, then the frequency of resonance of hydrogen comes out to be nearly about 60.0378 megahertz. That is, at a magnetic field of 1.41 Tesla, the resonance frequency which the hydrogen requires is around 60. So we can show here, that is gamma, which is gyromagnetic ratio for hydrogen 42.58 megahertz, and for carbon it is 10.71. This is a value for gamma. Now the magnetic field for hydrogens, that is, if this is the magnetic field, then radio frequency required is 60. If it is 1.88, then radio frequency required is 80, and so on. So the magnetic field strength, if varies, the frequency required by the hydrogen to flip for resonance also varies. And we can see here also, that is, if it is 1.41 magnetic field strength Tesla, then this megahertz frequency is required for a hydrogen to resonate, and if it is this amount, then this 300 megahertz is required. If it is 14.092 Tesla, then 600 megahertz is required, and so the amount for a proton to flip is different at the different magnetic fields. So different magnetic fields require different amount of radio frequency in megahertz to flip the hydrogen from a alpha spin state to beta spin state, that is lower energy state to higher energy state. That is, again we have shown, if we are now doing only hydrogen, if we take carbon also, then the comparison for hydrogen and carbons are, for hydrogen 1.41 Tesla 60 megahertz, 2.35 Tesla 100 megahertz, 7.05 Tesla then 300 megahertz, and for carbon the radio frequencies required are different. If it is 1.41 Tesla, that is same here, then for hydrogen 60 megahertz is required, but for carbon only 15.1 megahertz is required. So at different magnetic fields different values are required. So this is for the various nuclei for which the NMR spectrum can be obtained: hydrogen, deuterium, phosphorus 31, sodium 23, nitrogen 14, carbon 13, fluorine 19. For these there are different number of unpaired protons, unpaired neutrons, so net spins are these, and this is half integral multiple which we are doing, that is proton. If we generally also study carbon, for carbon again one unpaired electrons, for it is different, and therefore these frequencies required for flipping are also different. And this is also shown here, that is for 1 point for nitrogen this megahertz is required, for carbon 13 this megahertz is required, and for proton this megahertz difference is present in the energy states. So if we calculate the magnetic field strength, if we are given, that is radio frequency at which protons resonate or absorb, then we can calculate easily magnetic field strength. We already know that for 60 the magnetic strength is 1.41 Tesla required, so we can calculate that. And what magnetic field strength would be required to observe the NMR spectrum of fluorine carbon nuclei using the same radio frequency? So we know that this is a formula: frequency is equal to gamma over 2 pi b naught, and this is a gyromagnetic ratio, thus we already know. And for a particular nucleus for proton, its value is this. So b naught strength of magnetic field, and here is this formula, and putting these values, that is gamma is 360 into 10 to the power 6, because it is given, that is magnetic field in Tesla required to flip an proton nucleus in an NMR spectrometer that operates at 360 megahertz. So 360 into 10 to the power 6, and then 2 is, and for value of pi is 3.14 taken, and value of gamma is taken, that is 2.675. so b naught comes out to be 8.46. And similarly, what magnetic strength magnetic field is required when a 500 megahertz instrument is used for proton NMR? For that we can easily calculate the value. So next comes out to two ways of doing NMR experiment. As we have already discussed, we can change magnetic field or we can change radio frequency. So both can be changed, and this is shown here, is changed and frequency is kept constant. And the second, the frequency is changed and magnetic field is constant. So in the two ways, that is by changing the frequency or by changing the magnetic field, we can get the signals as such. For NMR spectrum, the use of solvents is very important. The solvent should be chemically inert, should not contain protons, should be non-polar, and should have low boiling point and should have low viscosity. That is, generally we use solvents that is like this: D3COOD, in which hydrogens are replaced by deuterium, and thus also hydrogens are replaced by deuterium. So first is the acetic acid. Like acetic acid, hydrogens are replaced with deuterium. In second is similar to acetone, in which hydrogens are replaced by deuterium, and this is ethane nitrile, hydrogens are replaced with deuterium. And this is benzene, hydrogens are replaced by deuterium, and so on. It is a chloroform, in which hydrogen is replaced by deuterium. And so we use such solvents in which hydrogens are not present, and they are chemically inert, they do not contain protons, are non-polar, and have low boiling points and have low viscosity. Any of these solvents can be used in NMR spectrum, and the which we use as a reference standard in NMR is tetramethylsilane. Tetramethylsilane is used as a reference standard because it is chemically inert and it gives a sharp line, that is a signal in spectrum, and it is magnetically isotropic. All the protons give a same signal, and they have a unique single line, and they are miscible organic solvents that they can easily mix with the molecule of which the spectrum is required, and they are readily volatile after the spectrum. So silicon is more electropositive than carbon, therefore pushes electron density towards carbon and thus to hydrogen, making methyl protons strongly shielded. So and this is a electropositive, therefore the electrons are pushed towards the carbon, and so all the protons Methyl protons are strongly shielded and they give a single signal because all are equivalent, and they give a signal and the signal given by them is taken as a 0. At the value given to the signal is 0 and others are compared with respect to that. So it is used as a reference compound or internal standard, and it fulfills all the conditions. It has a reference peak and calibration peak for chemical shift, and it has considered at 0.0 delta, that is, it is the starting from which we see the spectrums of the peaks of the other atoms. So it's all about the instrumentation and the solvent we generally use in the NMR spectrum. So thank you. We will continue with the other topic in the next lecture.